Okay, we'll get started again. So there's a question about the, okay, thanks. He's great. Question about law of multiple, it's not multiple properties, it's multiple proportions. And so let me back up a little bit and then we'll talk about that. And so the observations here were based on Lavoisier's observations. Lavoisier observed that delta M, delta M was 0. In other words, the mass didn't change for reactions. Reactions is often abbreviated RXN, and so reactions here. And so the total mass at the beginning of the reaction, we call that the reactants. This stuff we'll get more of. Since we don't have that much time in this, I'll throw in some stuff that comes from latter chapters. And the ending stuff we call products. So we start off initially with reactants and then we end up with products. So when we weigh out all the reactants at the start and then weigh out all the products at the end, the weight is the same, so no change. This is a pattern that's observed consistently for all reactions. Since it's for all reactions, we can make it a law. It's a very consistent, highly consistent. It's highly consistent. We don't want to call it a rule. A rule would have a lot more exceptions. So this is called the law of conservation of mass. Law of conservation of mass doesn't really describe things in detail. It's just an empirical equation. It's just a mathematical pattern. And so what we want is the fundamental description here. And so the tentative fundamental description for the law of conservation of mass, the hypothesis was that matter is made up of atoms, atoms here. This came from Dalton. Dalton proposed, atoms, people thought about atoms before Dalton's, but Dalton's atomic theory was the first meaningful atomic theory. The theory is different than a hypothesis. A theory has to do two things. One, a theory has to be well accepted. There could still be skeptics, but a well accepted fundamental description. During Dalton's times, there were a lot of skeptics. Because here Dalton's proposing atoms. What proof does he have? Well, this is his proof, law of conservation of mass. And so visually, what's happening in the law of conservation of mass, we could see here. And so atoms make sense in this particular reaction. Let me fast forward this.
Mercury 2 oxide.
Here. And so if matter consists of atoms, what's happening is the atoms just, all the atoms stay there. They're just rearranged, And so we don't lose any atoms in going from reactant to products. Products here being O2 and mercury, liquid mercury. And so it makes sense here. So this is why I bring up Dalton's atomic theory now, because this is a video in chapter 2. Dalton's atomic theory doesn't come until later. So we're just getting a little jump start here. Well, Dalton's atomic theory, theories have to do two things. One, accept the fundamental description. So the fundamental description of what's happening in the law of conservation of mass is all the atoms are there, they're just rearranged. That's it. But it also has to predict something new. And what Dalton's atomic theory predicted, the new thing, is this. Dalton's atomic theory predicted a new law. So what is that law? And so this predicted the law of multiple proportions. And the law of multiple proportions just says this. For example, like if you're on the low sodium diet, is it possible to get low sodium salt like this? Well, Well, in salt, there's one sodium and one chlorine. Sodium is Na, which was from natrium, and then chlorine, Cl. This is sodium chloride for this. But it's a 1-to-1 ratio. But maybe I want like a 0.7 to every chlorine. Is it possible to have 0.7 NAs to every chlorine? Well, not if things occur as atoms, because if I have a sodium here and a chlorine here, it has to occur as a 1-to-1 ratio. So in a salt structure like table salt, we have this. You know, salts like to form what we call lattices. This is a lattice. And a lattice does not consist of discrete molecules. There's no molecules in here in this lattice. There are only formula units in this lattice. And so formula unit is just picking any one of the black sodiums and any one of the these bigger chlorines here. And that would be a formula unit. So it's any one, it's not discrete as a sample of water would be discrete. Here, I just pick any one. So maybe this chlorine here. If I pick this chlorine, which of these sodiums should I pick? Well, it doesn't matter. We'll just pick with this one. And so that would be one formula unit. That's it. So what we see is we don't see this. You know, if matter consisted of infinitely divisible, then we should be able to put any amount of sodium, you know, 0.7, 0.71, 0.72, any amount of sodium in there, mix it with the chlorine. But if things occur as discrete molecules, then we don't see that. And so the same goes for something like H2O. And so the law of multiple proportions just says that compounds consist of, law of multiple proportions says that compounds consist of atoms in simple whole number ratios. Compounds consist of atoms in simple whole number ratios. And so we don't see this like H1.6, let's go, 1.60, you know, something like that doesn't exist. Does that answer your question for law of multiple proportions? Yeah, okay. So this is the scientific method. The scientific method starts off with observations. We take our observations of nature, quantitative observations, and then we find the patterns and the trends. If those patterns and trends are very consistent, then we can describe those mathematically using a law. And so mathematical equation is the most concise definition of that. Or we could explain it in words if we want to. But the law doesn't tell us what's happening, you know, at a deeper level. And so we hypothesize what's happening at a deeper level. So what if the mass is conserved? What does that mean? Well, what that means is a hypothesis. We come up with some hypothesis. And once that hypothesis has been thoroughly tested and accepted, then we elevate that to a theory. Sometimes there's a lot of work, and multiple scientists like Lavoisier started this part, but Dalton finished this part here. So in the video, we see it. Like I said, a couple of centuries worth of science in that video. Let's move on here. Did I start the recording? Yes, I did. Sometimes I forget to start the recording, so I have to be reminded. So that's typically what a scientist does, you know, to come up with a hypothesis. Think about this, you know, without taking any observations, could you have well, maybe you could have hypothesized atoms, but, you know, coming up with a hypothesis is very difficult unless you know the patterns of nature. You know, if you know the patterns of nature, or you've seen a lot of observations, then it's much easier to come up with a hypothesis. But to come up with a hypothesis cold, with no observations, would be something that would be terribly difficult, I think. Okay, moving on here. So, you know, if we think in terms, oh, would we call these formula units or would we call them molecules? Here. These occur as discrete units. Since they occur as discrete units, we call them molecules. Formula units can be used for both, though. Formula units can be used, this would be a formula unit of water, 2 hydrogens and 1 oxygen. It would also be a molecule of water. But we cannot use molecules for both, you know. Let me fast forward this. Back it up here. Okay, when I look at this, oops, come on. When I look at this, is there a discrete molecule there? No, there's no discrete molecule here. This is what we call lattice. And in this type of structure, you know, I could pick any of those and combine it with any of the others. And so in a lattice structure like this, you know, I have a whole bunch of formula units and there's no unique formula units. I just have to pick one red one and one blue one. So if I pick this red one, I have 4 different blues I can choose from. All of those are the same actually. And so I just pick one of them. And so I get 1 mercury and 1, and then I can build bigger crystals. With building bigger crystals, you just add more layers of mercury and oxygen onto that. And so here we can't, there's no such thing as a molecule in this case, because a molecule would definitely be a discrete thing. Whereas in water, it would be different here. And so here, when we look at this, we have different levels that we look at things, you know. Here's water, but we visualize water as pure substance. This pure substance has fixed composition and fixed properties. It's fixed composition, 2 hydrogens and oxygen. And we can visualize it at the particulate level, at the atom or molecule. Particulate just means the individual particle. An individual particle of this is molecule. This can be also represented by an equation like this. You know, we go H2O L for liquid. We don't spell it all out. H2O G for gas, you know. Symbolically, we're boiling water here. So we got that. That's chapter 1. There's no homework for chapter 1, end of chapter homework assignments. So let's move on to chapter 2. Chapter 2, I had to break up into multiple PowerPoints because of the videos. I ended up embedding the videos, so that's what took a lot of space. What happened to my chapter 2? Chapter 2, part 1. Oh, I see. That's what happened. I'm on 2 screens here. All right. Chapter 2 deals with matter and energy. So we're just going to continue. We'll talk a lot more about energy here. And so there are different scales that we visualize things here. One of the scales that we visualize things is the macroscopic. Macroscopic means you could see it with your naked eye. And so obviously, if we're at 1 meter, you know, a person's 1, 2 meters tall. You see a sheet of paper, which would be on the order of a decimeter, or 1/10 of a meter. Or like a wedding ring, which would be on the order of a centimeter, which would be 100th of a meter. Or like the thickness of a CD, which would be about 1 millimeter. We go from millimeters to even smaller stuff like a micrometer. You know, how big is a micrometer? You know, a micrometer is, this is wrong. What's going on here? Sorry. Oh, no. 100 micrometers, right? Sorry. 10 to the minus 4 meters is 100 micrometers. And so 100 micrometers, we're going to start needing a microscope. This is 10 micrometers is an animal cell. A bacterial cell is 1 micrometer or 1/1,000,000th of a meter here. And so optical microscope. When we go to a particulate level, and so people in Lavoisier's time had microscopes and Dalton's times had microscopes, but at this level we need something much more powerful, like a scanning electron microscope or scanning tunneling microscope, an SEM, scanning electron microscope, or an STM, or X-rays. X-rays can see. And so like virus particles are on the order of 10 to 100 nanometers. Nano would be 1/1,000,000th of a meter. You know, aspirin molecules on the order of a nanometer or 1/1,000,000th of a meter. Protein molecule here. Water is even smaller. Water is on the level of picometers. Pico is 10 to the minus 12. So the 100 picometers is 10 to the minus 10 meters, or 10 picometers would be an atom here. So these are individual particles. These are the smallest pieces of matter here. The smallest pieces of matter are going to be a molecule, an atom, or a what? Atom, molecule, or a blank will be the smallest pieces of matter, of at least smallest pieces of substances, I should say. Would be a molecule, atom, or a formula unit. That's correct. And so the smallest piece of water would be a water molecule. The smallest piece of gold would be a gold atom. And the smallest piece of salt would be a formula unit of salt. Does that make sense? So one of the first things that we look at when we're looking at matter are the states of matter, you know. And I wrote this on the chemical equation, the states of matter already. So as far as the chemical equation goes, we just use G for gases, L for liquids, and S for solids. These are the 3 states of matter. There's actually a 4th state of matter. A 4th state of matter goes like this. If we take a solid, and do you know the symbol for heat? There's a symbol for heat, which is a triangle. This is heat. If we take a solid and heat it up, we'll get a liquid. And so we'll take ice and melt it, get liquid water. And if we take a liquid and heat it up, we'll vaporize it or boil it into a gas here. If we take the gas and heat it up, we end up with the 4th state of matter. The 4th state of matter is called plasma. In the plasma, things are moving so fast, violently, that things get broken apart. Let me show you an example of plasma. Oh, shoot. Closed it. Well, you actually probably already know example of a plasma. This is one to watch this video again.
Mercury 2 oxide breaks down or decomposes readily when heated. Compare its mass to...
This is a plasma here. Yeah. So when we have a very, very hot gas, it can generate plasma. The sun is a plasma. It's a plasma. There. That would be the fourth state of matter. Just to be complete, or more complete. Chapter 2, part 1 here. I gotta start closing some of these windows, sorry. Okay. So we can look at these at different levels, you know. Here they're trying to show it at the particulate level. Obviously, these are so small, you can't see the individual molecules here. They're blowing it up so you could see it. And then looking at some of the properties, you know, this would be, is this a physical property or a chemical property? Shape. Physical or chemical? Yeah, it's a physical property, that's good. For gases, the shape is variable. It's the same shape as the container for gases. It's gonna fill the entire container, oops. Let me just, something with these annotations. Fix that. Liquids, they fill the bottom of the container. Solids, they're just rigid, constant. Volume is, gases have variable volume because there's empty space between, you know, between these molecules, there's nothing. And so the volume can expand, that is just have more empty space, or the volume can contract, have less empty space. Liquids, the volume touches, I mean, the molecules touch, there's no empty space pretty much. Everything's touching, so it's constant. Liquids are not compressible, what they say. Solids are, the volume's fixed as well, so just gases. And then they're looking at how the particles are moving. These are just moving in straight. I think about movement. There's three types of motion. The first type of motion is called translational motion. Translational motion is just moving from point A to point B in space. It can translate. And so these molecules can translate. They can move wherever they want. So we got translational motion. The second type of motion is vibrational motion. Vibrational. And it turns out these molecules in water at room temperature aren't static. The molecules are actually vibrating. So these hydrogen atoms are actually moving, you know, like this or like this. The hydrogen atoms and the oxygen atoms are moving. And so there's vibrations of the molecules themselves. And then these water molecules can also rotate, you know, as rotational motion. And so these are the three types of motion: translational, vibrational, rotational. In gaseous water, all three are present. The water molecules can translate, they can vibrate, they can rotate. However, in liquid, actually liquid, they can do all three too. They can translate, they can rotate, they can vibrate. In solid, they can't. In solid, we only have vibrational motion. And so in the solid state, the water molecules cannot translate and they cannot rotate. They're pretty much just stuck with vibrational motion. Particle spacing, here there's empty space. Here the particles touch, you know, they touch. And so liquids aren't compressible, and solids, they touch each other. And so you can't force them too close to one another. And so these are incompressible. We try to visualize this using the theory of chemistry. When we try to visualize this, let me clear these drawings here. We use something called kinetic molecular theory. This is particulate level visualization. Kinetic molecular theory, kinetic means motion. So let me write that in. Molecules are just molecules. And so this is motion of molecules. This is based. This is based on theoretical calculations about how this should move. I don't know what music they put here. This is in the liquid state. The water molecules, these purple lines here represent the what's holding the water molecules together in the liquid. You know, there's this fountain in downtown LA which shoots out gigantic drops of water. And these gigantic drops of water look like blobs, you know, and so a gigantic drop of water gets shot out and it's like a blob, just like this. It looks like it's trying to break apart, but it can't break apart into smaller little blobs. It just stays as this big blob here. And it stays as this big blob because something's holding the water molecules together and not letting them spread all apart. And what's holding them together are these purple things, these purple lines here. What this purple line represents is something called a intermolecular attraction. What did I do it? I did it wrong again, sorry. Do it this way. Intermolecular force, IMF, that's what we call it. And it's the attraction that holds the water molecules together. Attraction that holds the water molecules together. You can break that attraction by heating it up. You heat this up, it'll just break it and you'll vaporize it into the gaseous state. In the gaseous state, they aren't being held together. So water molecules together. In this particular case, this attraction is given a name. This attraction is called H bonds. And so H stands for hydrogen. And so hydrogen bonds are the attraction that holds these together. It's not a bond in the sense that these are permanently bonded to one another. Like if I look at the water molecules, like this water molecule, it's not permanently bonded to that. This attraction can break and we can set up H bonds to other water molecules. But this is just kind of a dynamic simulation of this. Let's take a look at this. So you can see the H bonds breaking and reforming, and then the water molecules can translate. This is slowed down, you know, there's actually a lot of movement here. They can also vibrate and they can also rotate. But the H bonds are kind of keeping it together, you know, preventing them from vaporizing off. If the H bonds weren't there, all the water molecules would just vaporize off, you know. But the H bonds are holding them. And again, these aren't permanent. Whereas when I look at the red and the white here, do you see that little stick? That's a permanent bond, you know. Hydrogen consists of water consists of 2 hydrogens, 1 oxygen. So that's permanently bonded into a molecule like this here. This is liquid water. This is ice here. Look at the water molecules here. These are H bonds holding them together. Now the H bonds aren't coated in purple. The H bonds are these red dashes. But in ice, you see the water molecules have a preferred orientation. And so ice has a very open structure. You can see there's a lot of empty space in ice compared to water. And this big empty space here. This is why ice floats on top of water. It's not very dense because it's got this open structure. And that's to maximize the H bonding interaction here when we look at the individual water molecules. What happens? Now this is vibrations here. And we're going to get more and more vibrations as we heat this up. So if you keep heating up ice, what's going to happen is eventually you're going to break those H bonds. They aren't going to be so perfect anymore. Here we have perfect H bonds. And here we're going to have less than perfect H bonds in the water because there's more random motion in water, and they got the translation. So this ice crystal is melting here on the surface. You can see it starting to melt here. So I'm fast forward this a little bit. So more of the ice crystals melting and more. Oops. Let's go back here. We aren't going to melt the whole thing, but you can see it's melted here at the bottom and the top. Here's another ice crystal with a different perspective. So they turn on the vibrations. Here the H bonds are shown by these dots, and that's what's holding the water molecules together. Okay, now that this is melted, this is liquid water. The molecules are still being held by H bonds. So if we keep heating this up, what's going to happen is it's going to vaporize. When it vaporizes, we're going to just break these H bonds and then allow the molecules to go free. And so right now, all the molecules are stuck together. But once you heat it up, then you can break it, and now it's a gas. In the gaseous state, we could have some H bonding interactions, but for the most part, these molecules are free to rotate, translate, and vibrate on their own. Here, they're stuck a little bit, a little cluster here, but mostly lots of empty space here. It's molecular. If you notice the structure of the water structure is very well ordered. When we have a well ordered structure, it's called crystalline. Like here, these would be 4 crystals, and each of these 4 crystals has a really well ordered arrangement of atoms here. And so we have crystalline solid. We could also have less ordered, like the liquid water was more amorphous, you know, there's a pattern. And so liquid water was more amorphous in terms of structure, but you know, sometimes we could get amorphous solids. That is, the solids don't have a really well-ordered pattern like in glasses. So that's that. And so ice forms beautiful crystals because of these well-ordered arrangements of water molecules. So we're looking at chemical and physical changes and properties. We looked at chemical and physical properties, right? And let's look at chemical and physical changes associated with that. And so if we look at change on the macroscopic level, chemical change, you know, the original substance is destroyed, you know, in the chemical change, and new substance is formed. We can see that macroscopically here. This is sugar. You heat the sugar, it caramelizes, and then eventually it chars. It just starts to burn like this, it's burnt sugar. And so obviously this is a chemical change because this doesn't taste like sugar anymore. Whereas a physical change, you know, would be the same. So if I had ice and melt it to water, it's still water. And if I had the water and boil it to steam, it's still water. And so there's no change here. And so in physical, different form of the same substance, that is a different state. Probably should say different state, or it could be it could be the same state. They're different ice crystals. There's ice 1, ice 2, ice 3, ice 4, ice 5. They're different ice crystals depending on the pressure. Okay, at the particulate level, we can see at the particulate level what happens here is the sugar completely changes its composition here. We start off with a reactant, sucrose. And we don't end up with sucrose anymore. We end up with charcoal, which is carbon, and water. We're here, just carbon deposits and water. Okay, so this chemical identity did change at the particulate level. New molecules are formed. In this case, carbon doesn't form molecules. Carbon forms a lattice. And then formula unit would just be a C here. Water would form molecules here. At the particulate level for physical, nothing happened. If you look at the water molecules, they're all there still. Here's an example of a chemical change here. You know, the smallest piece of water we can have is a water molecule. If we try to break that down into smaller pieces, it's no longer water. Well, water, one way to break it down is via chemical change or chemical reaction. In this case, the chemical reaction is called an electrolysis reaction, which is a redox type reaction, which we'll talk about later. And so let's watch this video on the electrolysis of water here. I don't think I did the audio to this, but let me see. No, this video is a little bit long. So we could do electrolysis with 9 volts. So they stuck some thumbtacks in this plastic cup and they placed it on this 9-volt battery here. Okay, the electrolysis process is started. Sometimes they'll put some salts in here or some acid or something to help it speed it up. But you can see that the water is starting to decompose here. And when water decomposes, it decomposes into oxygen and hydrogen. Oxygen's a gas and it's O2. Hydrogen's a gas and it's H2. These like to pair up. And so it turns out that oxygen's formed at one of these and hydrogen's formed at the other. Let's see if we could figure out which one is which. Which one do you think is the oxygen? Which one do you think is the hydrogen? Back. Oops, this was wrong. I thought I edited this video, but let me see. Okay, I got rid of the audio. Okay, let me pause it here. Can you tell which one's hydrogen and which one's oxygen? I can. What would you guess? If you had to guess, which one would be the hydrogen, which one would be the oxygen? Okay, on the left, oxygen or hydrogen? Oxygen, so this is oxygen. And on the right is hydrogen. How do I know? Because I formed twice as much hydrogen. You know, for every oxygen, I'll get 2 hydrogens. That just comes from the decomposition equation. So if I look at the equation, I'll take 2 waters just to keep it what we call balanced. This is going to make 2 hydrogens for every 1 oxygen. It's gas, that's gas. And it forms at different electrodes. So they're doing it fancy. They're using fancier batteries and they're using platinum electrodes, which are expensive. Those are nice. The platinum electrodes rather than thumbtacks there to, because this is using electricity to break up the water. And so here we're using electricity. And so over here, they're forming oxygen, and we can see that the hydrogen is going to be twice as much here than the oxygen. Okay, so that's using a chemical technique to separate the hydrogen and oxygen from water, but it's no longer water once we do that. Now we can break up these atoms. We can break up these molecules. These are molecules here. We can break them up into smaller species, which are just the atoms, and then we can try to break up the atoms and they're going to behave differently. All right, let's look at what we're looking at here. Yeah, chemical change. This is a chemical change. Look at pure substances and mixtures here. This is another thing that likes to pair up. These are called diatomic molecules, 2-atom molecules. A bromine, and this is pure bromine, which is liquid. And so there's translational, rotational, vibrational motion here in liquids. And so it's just moving around. This is pure liquid water. So again, the molecules are touching. No, they don't show them touching, they are touching. There's no empty space there really, or minimal empty space. And moving, rotating, vibrating, and translating. That's pure. Here's a mixture. This is what we call low concentration. That is, in other words, it doesn't have much bromine in, so it's dilute mixture. This is a more concentrated mixture. You can tell by the color too. The dilute one would be more colorless, whereas the more concentrated one would have a deeper color. Bromine's orange, red-orange kind of color. And so it just shows more bromine. Here, how many bromines do I have? 1, 2, 3, 4. Here I go 1, 2, 3, 4, 5, 6, 7, 8. This is twice as concentrated than this. And so the composition changes. This is going to have fixed properties, fixed composition. This has fixed properties, but bromine water has variable properties depending on how concentrated it is. And it has variable composition because we can change the amount of bromine there is in there. And so these two are classified as mixtures here. And mixtures will have variable composition and variable properties depending on the composition. Okay, that's in part 1. Let's go to part 2 of this PowerPoint. All right, so part 2. Let's look at this whole idea of fixed versus variable properties. Example of water. Water has pure water has a fixed boiling point of 100 degrees C under normal conditions. And so no matter, you know, how long you heat it for or how much heat you use or how much boils off, it's fixed. And so we warm up the water until it gets to boiling, and then once it's boiling, then the temperature stays fixed. However, salt water, or solutions in this case, solution would be a mixture. Solutions are, let me just tell you what, solutions are homogeneous mixtures. And we could have liquid solutions, solid solutions, gaseous solutions. Air would be a gaseous solution. Salt water would be a liquid solution. Brass would be a solid solution. So we have different solutions. Well, this would be a liquid solution here. So in this case, the liquid solution boiling point depends on the composition. So as more and more water vaporizes, it becomes more and more concentrated. The salt doesn't vaporize so easily, just the water vaporizes. And as it becomes more and more concentrated, that means its boiling point changes. The boiling point is going to depend on the concentration of those. So let's check out this video here. In this video, I didn't do the audio for this, but water is boiling. This is a little bit miscalibrated. It's boiling at 99. And then they dump in salt in here. Let's look at what happens. What happened to my video? Initially, when they dump in the salt is at room temperature, so it cools down the temperature a little bit. But when it comes back and starts boiling it again, it's boiling at a little higher, you know. Now it's boiling at 100 rather than what it was before, you know. And so that's what's going to happen. And so why is it changing here? It's changing here because as more and more water vaporizes, the solution becomes more concentrated. So it becomes increasingly concentrated. Solution becomes increasingly concentrated. Concentrated. Let's look at this here. And so the boiling point, this is what we call boiling point elevation. You know, salt water has a little bit of elevated boiling point, that is elevated temperature. Here. The next example is this problem from the book. In this problem from the book, we look at liquid A, liquid B, liquid C, before freezing and then after freezing. So before freezing, what is its density and its specific gravity? So before freezing, liquid A had a density of 1.08, liquid B has a density of 1.00, and liquid C has a density of 1.12. And then what they did was they froze it. And when they froze it, only the water freezes. And so interestingly, when you freeze salt water like this, what gets frozen here is just pure water. And so this would just be ice. And this ice is not salty. Oh, this ice is just like regular water, pure water. And so just the water, the salt doesn't get frozen out. And then what they did was they removed the ice. And so after freezing, they removed the ice. And then they checked the density again. So they'll have the density before. Actually, here, this is salt water. And then we'll freeze it. And so they have the density here. So the density is 1.08 here, for, let's say, the first one. And then they freeze it, and they form a crust of ice. And then they remove the ice, and they're left with salt water here. Well, it turns out they're left with salt water. The density's gone up a little bit because we've lost some water. The ice is pure water, pure H2O. And so it freezes that. So take a look at this data here and then see what you can conclude. I'm going to give you a minute to think about that and pause the recording. Here. All right, and so in this case, why did the density increase here? Why the density increase is because we have a mixture here. Salt water consists of salt and water. If we remove some water, okay, so they form some ice, which is pure water, and they remove the ice. If we remove water, then it's going to get saltier. If it gets saltier, then the density increases because we have more salt in the water. Pure water has a density around 1. And so, yeah, liquid A is salt, it's getting more salty. Liquid C, the same thing. Liquid C is getting more salty because we're removing the ice. But with liquid B, we remove the ice and the density didn't change. So what can you conclude about liquid B? Yeah, liquid B is a pure substance. And so for this has got to be pure or substance. Its composition doesn't change. Whereas A's got to be a mixture, and C's got to be a mixture. And so that's what we conclude. Yeah, not a mixture, that's correct. Good. Yeah. All right, let's see what we have next here. Okay, when we have mixtures, we have kind of 2 types of mixtures here. Or actually, it doesn't even have to be a mixture. We have homogeneous and heterogeneous. These apply for both mixtures and pure substances. You know, even pure substances can appear a little bit heterogeneous. Homogeneous means uniform in appearance. Heterogeneous is non-uniform. And so typically pure substances are uniform. So pure substances are homogeneous. Here we have the pure substance water. It's very homogeneous. So it's what we call a CCS. Does anybody know what CCS stands for? It's an observation, although it's kind of hard to see because of the background here. The background makes it a little weird. CCS stands for clear, which clear just means you can see through it, but it doesn't mean it doesn't have a color. And so we have to add in the color. The color is colorless. And S stands for solution. Solution is a homogeneous mixture. Solutions are homogeneous mixtures. Except this is not a solution, this is pure, so we shouldn't call it a solution. Homogeneous mixture. So I have this wrong. A solution is a homogeneous mixture, so this should be the CCS, not there. This should be the CCS, the last one. This should be a CCl. A CCl stands for clear colorless liquid. Water is a clear colorless liquid. This is, do you know, this is alcohol. This is ethanol. ethanol. This is alcohol in alcoholic beverages. It's also the alcohol that they use in gasoline. Don't drink gasoline though, because lots of poisonous stuff in there. About alcohol is non-poisonous in moderation. Okay. But that's a CCl. It's a clear colorless liquid, and then we form a CCS. So we take our water and mix it with the alcohol. We get alcohol water. This is a CCS, clear colorless solution, because a solution means it's a homogeneous mixture. So this is a homogeneous mixture of water and alcohol. And when you look at it, you can't tell. I mean, it's uniform. It looks the same as both of these here. And the only way we knew it was a solution is because we mixed it together. Otherwise, we don't know if it's a solution or not. We could use properties to determine the solution or not. You know, we could try to use separation techniques as well. Here, this is not a solution here. There are two distinct layers here, the top layer and a bottom layer here. And both of those are liquids. So let's take a look at this one here in the video. Let's see, did I do the audio? I guess I didn't do the audio. This is oil. Oil is less dense than water, so oil floats here. And this is water on the bottom. So you can see the oil layer on the top, the water layer on the bottom here. They don't like to mix. Oil and water don't mix. The reason is because of the intermolecular attractions. Water likes to be around water because of hydrogen bonding. Hydrogen bonding is very favorable. Oil doesn't hydrogen bond, so oil might try to fit in with water. Here, these are representative of oil. Oil is actually much bigger usually. They're using these molecules to represent oil here. And water, they try to mix it together here in this simulation. So looking at this mixture of oil and water, they're using a molecule called pentane to represent oil, but oil is usually a longer, bigger molecule. This is going to be kinetic molecular theory. Kinetic means what again? Yeah, good. Current motion. So they start this. Let's go ahead and watch this simulation. Note the scale. This is in picoseconds. You know what a picosecond is? It's like a trillionth of a second. So they slow this down. You know, if you took 1 second and you could count to a trillion in 1 second, then one of those would be a picosecond. But eventually what happens is the water doesn't like to mix with water, and so forces the oil out. Water likes to hydrogen bond with other water molecules. And so water likes to stay with water or other things that hydrogen bond. And so you could see it's separated into two here. And this would be heterogeneous. This is heterogeneous. These are homogeneous here. All right. Homogeneous and heterogeneous apply to both, you know, substances and mixtures. But oftentimes when we have a mixture, we like to separate it, mixtures out. And so if I had the salt water mixture, how do I separate the water from the salt? Well, one way of separating salt water is by distillation. And so what you could do is you could just boil off or vaporize the water. The salt takes much more heat to vaporize, so the salt stays in the flask here. This is a distillation flask. This is what we call a round bottom flask. Round bottom flask has to be supported by a clamp here or some kind of dish down here otherwise they don't stand up by themselves. But the advantage of a round bottom is it distributes the heat more evenly. And so we have this round bottom flask, I think. And then what they're trying to do here is vaporize the water. So we get water vapor. The water vapor goes and touches this tube here. This tube is cooled. This is a double-walled construction. On the inside wall, we have the water vapor. On the outside wall, we have cold water running through. So you put cold water running through. This is called a condenser tube. And what happens is when that water vapor strikes the inside, it's going to be cold and it's going to condense into liquid water, and we get pure water. This is called distilled water there. Distilled water. This is very energy intensive because you have to boil the water. Boiling water costs you a lot of energy. And so distilled water is expensive. And so this is distilled water. Because of the cost of distilled water, well, we don't use it in our labs. In our labs, we use something called deionized water versus distilled water is given the symbol DW versus deionized water. Deionized water isn't going to be as pure, and but it's a lot cheaper, and it's given the symbol DI. DI for deionized, DW for distilled water. And so this is very pure water. And so this is what we call separation of mixture. So if we have salt water, we can separate the water from the salt by distillation or vaporization. Here's another mixture. This is a mixture of a solid and liquid. This is very common type of mixture. We can separate the solid from the liquid by filtration. So filter paper, when you buy it, comes in a circle like this. And then you got to make that fit into a cone. So we got a flat circle, and you make it fit in the cone by folding it and folding it. And a lot of people tear off an edge. I don't know exactly why, but I was taught this: tear off an edge. I've done it both ways though, too. Sometimes I decide, no, I'm not going to tear off an edge. It works fine. Anyway, they pour the liquid phase through there. The liquid gets poured into the beaker. The solid gets stuck in the filter. That's filtration. These are common separation techniques. These are physical separations here. Chemical separation would be like electrolysis that I showed you earlier. Electrolysis of water. Let's see. So I think we came back on break on the last one a little after 3. All right, so I think it's time for our next break here. So let's take another break, and then we'll start up again. Is it time for our break? Been about an hour, hasn't it? Yeah, okay. So I'm gonna pause this. So if there are no questions, then let's continue. I have some other examples of separation. So again, physical separations. We have one other type of separation, which is the chemical separation. And the chemical separation was used to separate hydrogen from oxygen in water. Do you recall what that technique was called? How do you separate hydrogen from oxygen in water? Well, we have to use a chemical separation, and that chemical separation had a name. Does anybody remember the name of that? Yeah, water electrolysis. Electro for electricity and lysis for breaking it apart. And so that's correct, right? Great, that's good. Let's take a look at another separation. This is a very simple one. Let's watch this video here.
Common breakfast cereal is added to a beaker. And milk poured in. The beaker contains a magnetic stirring device that is used to stir the mixture, and the mixture is stirred for a long time. When the magnet is removed, metallic iron is seen on its surface.
Okay, this magnet that they use with the magnetic stir here is coated with this white plastic that coats. There's a magnet inside that white plastic, and this white plastic is Teflon. The reason they use Teflon is because it's very unreactive, and so it's not subject to chemical attack. Whereas if they use the magnet alone, then the magnet could be eaten away by whatever they're mixing. And so this is called a stir bar. And the stir bar you place inside this piece. Do you know what this piece of glass is called here? This is one of the most common pieces of lab equipment. And a beaker, good. So you guys are familiar. This is a beaker, which is just a cup. And beakers are usually made out of Pyrex glass. Pyrex glass is pretty tough, but still you can chip it and shatter it. And so you gotta be careful with it. And so what they did was they put the cereal and this homogenized it. It was very heterogeneous earlier, and they homogenized it to what they're doing is they're trying to separate out. There's, you know, it's iron fortified cereal, so they're trying to see how much iron they can get out, or just not how much. They're not doing it very quantitatively here. It's just qualitative. This is a magnetic stir. This is a magnetic stir, but it has another knob here, and so it's also a heater. And so this is a ceramic topped heater and a ceramic top magnetic stir. And so stir knob on the right and a heating knob on the left. And they didn't heat this up though. So that was just left at 0. This bar here is just Teflon with a little magnet at the end so they can extract them. Usually what happens is people dump it down the sink and they end up tossing the magnet in there. Then you can see that this is the iron that was in the cereal here that they captured using the magnet. And so they used a magnet. Iron filings, one of the physical properties of iron is that it's magnetic. It's it's what we call a ferromagnetic material. And so it's got a permanent magnetic moment. So there's some iron. We could weigh that out. You know, you can scrape that off the Teflon stir rod, weigh it using a very sensitive, what we call a balance. A balance we use to weigh objects, and then figure out how much iron was in that cereal if we pre-weighed the cereal before homogenizing it like that. Okay, that was the end of that video. Let's take a look at another separation here.
Water, sand, and copper sulfate create a heterogeneous mixture. Filtering separates the sand from the water and dissolved copper sulfate because the sand is not soluble. To separate water and the dissolved salt, the water must be boiled off. Leaving only the solid.
All right, I guess that's the end of that video. And so they use 2 techniques: filtration to remove the sand, and then boiling to remove the water. If they used a distillation apparatus, they could collect the water. And the water that they collect from the distillation, you should be able to drink it. It should be pure. That's because all the copper, this is called copper 2 sulfate, all the copper 2 sulfate stays down here. It takes a lot hotter temperature to vaporize this stuff off versus water. Water is going to vaporize off at 100 degrees C. And so we could have captured that, and then we could have had pure water, which would have been potable, drinkable water at the end. We had distilled it. Here's some more examples of pure substances. I'm going in the order of the book here. Pure elements and compounds. When we're dealing with a pure substance, it's got fixed composition, so it's not a mixture. And if it's not a mixture, it's going to be an element or a compound. Compound is going to be 2 or more elements that are bonded together. This is sodium chloride. Would we call this a molecule of sodium chloride here? Would you say yes, that's a molecule? Or, oh, sorry, I missed the question here. Never mind. The process of the milk and cereals is it doesn't really have a name. It's just using a magnet to extract the iron out. And so it's not really the tricky thing would be separating the rest of that. You know, the milk cereal mixture. How are you going to separate that? You know, separations are a very big challenge in chemistry. We often deal with mixtures. And so a couple of big challenges. One, how do you know it's a mixture? That's one. Two, you know, if it is a mixture, how do you separate out all the components? Well, the second video is easy. The first video, they didn't. All they did was they got the iron, but how do you separate everything else in this mixture here? That would be really tough, really hard to do. And so what they ended up with is they ended up with pure iron, oops, and some homogeneous or relatively homogeneous mixture at the end. You know, there's the pure iron, but you know, this stuff is not pure. That's not pure milk cereal. You know, that's some kind of weird. In this case, they ended up with 3 pure substances. What are the 3? Well, sand. It depends on the sand. You can buy pure sand. If you buy pure sand, it's quartz. But most beach sand isn't pure. It's heterogeneous. So there are lots of different minerals and even rocks and beach sand. Rocks are mixtures. Did you know that? Rocks are mixtures. Minerals are pure substances, compounds usually. Rocks are mixtures of minerals. So sand is going to be a mixture usually, unless you buy the very pure stuff, which is just quartz. And then we left with this mixture of copper 2 sulfate and water. And then they separate that into pure water, which we boil off. And then down here, even though it looks heterogeneous, this doesn't look so homogeneous, but this is pretty homogeneous. Once it's completely dry, it has this powdered baby blue color, and it'll be pretty uniform throughout. If you crush these crystals, it'll look pretty uniform throughout, and that would be the pure copper 2 sulfate. And so we have elements and compounds. You know, for pure substances, the composition's fixed. And I should write that down here. The composition is fixed. And so the composition of salt here is 1 sodium, which is natrium, sodium, and 1 chlorine. And so is there a molecule of sodium chloride? No, there's no molecule. I just see a formula unit. You know, this would be formula unit here. Or you could pick this one, or you could pick this one, you know. Well, 1 formula unit is just one of these gray ones and one of the green ones. The gray one's the sodium, the smaller one. The green one's the chlorine, the bigger one here. So this would be a tiny, tiny crystal of sodium chloride here. And the smallest piece of sodium chloride you could get is 1 formula unit. Doesn't occur as discrete molecules. This is methane down here. Methane has 4 hydrogens and 1 carbon, so it's CH4. That would be its composition, 1 carbon, 4 hydrogens. We call this a formula. And since it occurs as molecules, we call this a molecular formula. We also call this a formula, but we would not call this a molecular formula. You know, we'd call this what we call an empirical formula. Empirical formula, but I'll talk about empirical formulas and molecular formulas later. Looking at this, there are different ways of representing the structure of this. This is called just a stick drawing, or you know, simple perspective drawing here. But we often don't even get that fancy. You know, most people will just show that we have a carbon and that's attached to 4 hydrogens, and they'll show the attachments as bonds, as a single line like that. This is trying to put it into 3D like this. This is called a ball and stick model. This is a space filling model because the atoms are actually touching. Not only are the atoms touching, they're kind of overlapping like this. Do you see that? They overlap. This is an overlay of the ball and stick with the space filling. You know? Ball and stick is so you can see the atom bonding arrangement more clearly. Different ways of representing that. But this would be pure methane, which is a gas. And so it consists of a whole bunch of these molecules. This is the smallest piece of methane you could have, which would be a molecule of methane here. Okay, let's go on here. Some examples of compounds, elements. Here are common household compounds, like baking soda, quartz here, Rolaids, I don't know, Rolaids, formula. Lye is sodium hydroxide, calcium carbonates, chalk, or magnesium carbonates, chalk, etc. Here's some elements. These are supposed to be elements like copper on the penny surface, graphite, which is carbon in the pencils, lead, which is a fishing weight. This looks like copper wire here. These are zinc-coated iron here. And so this doesn't look like iron, but it looks like zinc. This is galvanized. Silicon, gold or silver, I don't know, or platinum. This is probably gold, a layer of gold underneath. This is silver here. Silver occurs as a lattice like this. The smallest piece of silver would be a silver atom, just one atom here. Yeah. And so silver occurs as crystals as well here. Sodium, we have this type of structure. This type of structure is a metallic lattice like this, where the sodium's. Barium is metallic lattice. Smallest piece would be the atom here. This is what silver metal looks like. You don't want to touch it with your hands. It's very reactive, especially with air and water. Barium, here. This is just finely divided barium. Hydrogen likes to pair up, H2. This is diatomic, colorless gas. Oxygen, O2, colorless gas. Chlorine has a color. It's yellow, green. And it's also diatomic. It likes to pair up. Chlorine atoms are bigger than oxygen. This is something called hydrogen chloride, a hydrogen atom and a chlorine atom. It's also a gas. It's also hydrochloric acid, known as. Water, we know that. Sodium chloride, this is the lattice. This would be a small crystal of sodium chloride. That's a formula unit. Barium chloride is also a salt lattice like this, sodium chloride, but it has a different structure, you can see there. Both of these are white, but when you look at the little crystals will be a little bit different in terms of shape, that kind of thing. What would you call this? What would you call that? Would you call it, let's start off trying to characterize matter. So let's try to characterize matter. Would you call it solid, liquid, gas? Solid, liquid, or gas? It's a gas, yeah. It's got to be a gas because these aren't touching. There's gaps here, big gaps. So it's got to be a gas. Would you say it's pure or a mixture? Yeah, this is pure. And would you say that this forms atoms, molecules, or lattices? Atoms, molecules, or lattices? Yeah, molecules. In fact, you know what I think this is? I think this is P4. Although phosphorus doesn't have a gold color like that, but I don't know why they use gold. But this is P4. This should be white phosphorus. White phosphorus. That's what it looks like to me. White phosphorus, it's P4 because phosphorus likes to cluster in these 4 atom molecules. And so that's why it's called P4. That was part 2. Let me go to part 3. I had to break it up into 3 parts because the videos take up a lot of memory. Let me make sure it's recording yet. All right, solid, liquid, or gas here. Gas. Pure or mixture? Looks like everybody's saying it's a mixture. I don't see it as a mixture. When I look at this, this has pretty much a fixed composition. You know, black, you probably don't know this, but there is a rule for the colors. The rules, of course, are going to have lots of violations, rules. But black is usually carbon. It's a carbon, which has the symbol C. And then this is supposed to be white. White is hydrogen. H. And so what is the composition of each of these? In other words, the composition is given by the formula. And so we have 1 carbon and 4 hydrogens. So we call it CH4. CH4. CH4 has a name. Do you know the name of this? Methane. That's correct, Adrian. That's good. Oh, this is methane. Methane, this is pure. And so this is pure methane. It's a gas. And it consists of methane molecules, right? Is this atoms, molecules, or lattices? This is molecules. And these are discrete molecules of methane here. So it's pure methane gas. Okay, what's this? Solid, liquid, or gas on the left? That's okay. I would say it could be either, but looking at how well ordered it is, I would say it's a solid. You know, liquid would show more disorder than this. This is so well ordered. I'm going to say it's a crystalline solid. And then it's going straight to a gas. This process is called sublimation. Sublimation. Sublimation goes straight from a solid to a gas, like it doesn't melt into a liquid. And so there's certain things that do that. So just a second, I'll just take care. Okay, how did you tell if it was a mixture or pure substance? Methane? I could tell it's pure because there's only 1 species in here. And since there's only 1 species in here, a mixture would have to have 2 or more different substances in here. There's only 1 substance in here, and that's CH4. And that's how you can tell. Is this pure or is this a mixture down here on the left? This is pure too. There's only 1 substance. It's this, it looks like we have 2 atoms paired up. And so I know it's purple, iodine. Iodine likes to pair up like this. And so this looks like the sublimation of iodine. Iodine has the symbol I, and it likes to pair up. So we form molecules of I2. And so this would be solid, I2 solid. Over here, is this solid, liquid, or gas? On the right. Yeah, this is a gas. So we're going straight from a I2 solid to I2 gas. In terms of a chemical equation, we just write I2 solid goes to I2 gas. And that would be called sublimation. Here. Is this a physical change or a chemical change? Yeah, dry ice does the same thing. Yeah, this is a physical change. You know, it stays iodine. It's just in a gaseous state instead. So that's good. Let's take a look at the next one. Here. Okay, over here on the left, solid, liquid, or gas? Yeah, this is a gas for sure. Is this pure or a mixture? It's pure, yeah. This looks like, are these molecules, atoms, or lattice? On the, these are molecules. And it looks like diatomic again, and what's green would be, you know, my guess is that, and this is, it's a rule, it's not a law, you know, a law, we'd have to strictly adhere to it. But this looks like Cl2. Do you know what Cl2 is called? Like O2, what's O2 called? O2 is called oxygen, Cl2 is called chlorine. So this is chlorine gas. Chlorine gas. Okay, on the right, is that pure or a mixture on the right? This is also pure, right? Is it atoms, molecules, or lattices? All right. These are atoms. And so it looks like what's happened here is we did this. We went from diatomic chlorine or chlorine molecules to atomic chlorines. So every molecule I break apart, I end up with 2 chlorine atoms. And so if I break apart a chlorine molecule, I get 2 atoms in the gaseous state. And so what I've done is I've broken apart, well, chlorine doesn't like this. Chlorine likes this. And so this is unstable here, unstable. This is more stable, but chlorine isn't so stable anyway because chlorine's pretty reactive. And so even in diatomic form, it's not the most stable stuff. But compared, I'd much rather, if I were to inhale a breath of chlorine, I'd much rather inhale diatomic chlorine than atomic chlorine, because atomic chlorine, you know, is quite a bit more reactive than diatomic chlorine. Can I ask you, is this a chemical change or a physical change? Chemical. Yeah, that's correct. This is a chemical change, you know. These 2 species, even though this is pure chlorine on the left, this is pure chlorine on the right, their properties are a little different. And this stuff is much nastier, the atomic chlorine, right? Because it's a little less unstable. I mean, it's a little less stable, making it more unstable. Sorry. Clear those. Let's move on. Is this a solid, liquid, or gas? Solid and liquid, those are both correct. It's not homogeneous. If it's not homogeneous, what do we call it? Hetero. Yeah, this is heterogeneous. This is ice water. And so we got ice cubes dissolved in liquid water, or just placed in liquid water. They aren't dissolved, they're just sitting there. So ice water. Is ice water pure, or is ice water a mixture? Pure. Yeah, in one sense it's pure. I could go with either answer for this, you know, because on the one hand, it's pure. You know, ice consists of H2O in the solid phase, and water consists of H2O in the liquid phase. So it's just pure water. And so on the one sense, it's pure. In the other sense, it's a mixture because we have a solid liquid mixture. And so I could go with either answer for this. You treat it. Okay, let's see. What's next? Is this the ivory dishwashing liquid? Is that a solid, liquid, or gas? Well, obviously it's liquid because they're telling you it's a liquid. Is it homogeneous or heterogeneous, this liquid? Okay, I would say it's homogeneous because it looks uniform. You know, it doesn't look non-uniform. It looks pretty uniform. So uniform, if it looks uniform to your eye, then it's homogeneous. If it's homogeneous, then we have two choices. Is it homogeneous pure substance or homogeneous mixture? Okay, so I see a lot of answers there. And so what's the key distinguishing feature between pure and a mixture? Well, one key distinguishing feature is this. Pure substances have a fixed composition, whereas mixtures would have variable composition. So does ivory, let's say each batch, like say, you know, let's say you're making chocolate chip cookies. Is each batch identical in composition to your previous batch? No, and so that's a mixture. Well, then you ask yourself this, does each batch of ivory have identical composition to every other batch of ivory ever produced? What would your thinking there be? That would be great if they did, but in terms of practically speaking, do you think they can hit it exactly the same? You know, and that is to the atom. Like H2O is always two hydrogen atoms, but what if one extra water molecule came in here, or what if one extra molecule evaporated off? Then its composition just changed, right? And so the answer is no. This is going to be some variation here. This is a mixture. This is kind of tough because they want it to be consistent. They want it to be exactly the same, but you know, it's a challenge to do that. It's like gold. You know, we have different names like gold. If we think of 24 karat gold, is that pure or is that a mixture? Yeah, 24 karat gold is pure gold. There's no problem with that. What about 18 karat gold? Is 18 karat gold a mix? Yeah, it's a mixture. Now, you wouldn't call 18 karat gold pure, would you? Well, you might be tempted, no, but the answer is no, because the situation is who made it? Who made that 18 karat gold? You know, and let's see what the constraints for 18 karat gold are. You know, when you buy 18 karat gold, are you getting as much gold as you should be getting? And so what is 18 karat gold? So let's take a look on Wikipedia or something like that to see if we can find out what 18 karat gold. No, I guess I won't go to Wikipedia. I'll just go to this link. This is the first one that came up. Okay, so in terms of composition, this is what 18 karat gold should be. 18 karat gold should be 75% gold, 25% other stuff. The other stuff would be zinc, copper, nickel, etc. So we should get at least 75% gold. Do you think whoever makes this always gets exactly 75? No, there's going to be slight variations, you know. Sometimes there might be a little bit more, which I kind of doubt, but most of the time there might be a little bit less than 75%. There's a little bit less, maybe they call it close enough. So let's say you got 74.5%. If you got 74.5% gold, Can you call it 18 karat? I see most people say no. But when we look at it, if this is the criterion, then yes, we can, because what does 74.5% round to? If I were to round this to what we call 2 sig figs, this is called 2 sig figs, by the way, this rounds, well, if it's 0.5, we got to round that up. And so 74.5% rounds up to 75%. So if somebody's making 18 karat gold, they're always going to try to hit 74.5%. That way they can maximize their profit, you know, in making it. Do you think they're going to make it like this, 75.4%? If I had 75.4% gold, what does that round to? That rounds to the same number. And so if you're making this stuff, what would you, well, it depends, you know, if you want to be generous, hit it at 75.4%, give them a little bit extra gold. If you don't want to be generous, then make it at 74.5%, because both of these round to 75%. And so this is what we mean by mixture. Mixture has variable composition. It's not fixed. And so its composition can vary, and then that means, but to call 18 karat, I'm sure there's some range, you know, that's acceptable. In this range that's acceptable. Probably the people who are very precise always lowball it here. Meaning that they give you a little less gold than what you pay for. What's this, solid, liquid, or gas? We got a lot of gases. Is this pure or mixture? It's pure, and then it's atoms. So, you know, this could be, even though this is gold, this could be gaseous gold, but who vaporizes gold? You know, you're going to lose the gold. And so we'll just call this, maybe this is like, some gases don't like to pair up. Can you name one gas that doesn't like to pair up? Actually, there are a lot of gases that don't like to pair up, but I'll tell you one gas that doesn't like to pair up. Helium. Helium doesn't like to pair up. It likes to be alone. And so helium gas would be something like this. Argon, xenon, krypton, those gases don't like to pair up. And so this would be something like helium gas, which is pure and homogeneous. Those are noble gases. That's correct, Ezra. That's good. Noble gases are characterized by their chemical properties. One of the chemical properties of noble gases is they're very unreactive. They're very stable. They don't like to react with anything. Maybe this is getting closer to a liquid, you know, because the distances are getting a little shorter. And so maybe these are kind of touching each other. So this might be a liquid. If it's a gas, it's quite a dense gas because there's very little empty space. Normally in a gas, we have huge distances compared to the size of the atom, you know, between them. And so this could be a liquid here. Is this a mixture or pure? Yeah, this is a mixture. And so a mixture means we could have any amount. So if I put another red atom in here, no big deal, you know, but I just changed the composition. If I put another gold atom in here, no big deal, or I can have any ratio of those. And so that's what distinguishes a mixture from a compound. A compound, you can't just do that, you know, just add another hydrogen to your water. You can't do that so easily and call it water. Okay, let's go on to the next one. What's happening here? This looks like a sublimation. So here we have a solid. I'm looking at this. This looks like a crystalline solid down here because it's pretty well ordered. Although this might be a liquid because, you know, it's just atoms, and atoms packed together quite nicely. we've got to see the motion, because what's going to tell us is translational motion, you know, translating from point A to point B. But again, this looks like either vaporization or boiling if this is liquid, or sublimation if this is solid. I'm going to gas up here. Okay, let's move on here. This is a gas here, but here I can't tell, you know, if we're looking at it side on. You know, are we looking at it like from here so we can't see the other atom because it's superimposed, or is this a mixture? Kind of looks like a mixture. You know, we have 3 of the diatomics and 3 of the singles, so it looks like a mixture. All right, let's look at some of these visualizations here. The green, what does that look like to you? How would you describe the green? I would describe this green as being a solid, or maybe it's a liquid, you know, but this one looks more liquid-like here. There's variations in the gaps, and they're close enough to be touching here. They have it slightly separated, so I guess you can see it better. The purple here looks like a liquid or possibly a gas, but a gas you'd expect it to be spread out more, so I'm thinking it's a liquid. And so here we have a solid and a liquid here. Here is gas, sure. Here, the C looks like, what, the green looks like a liquid, like I said, and the purple here would look like a liquid. So this looks like a liquid. And there's what we call a boundary here. At the boundary, so this is what we would call a heterogeneous mixture. Heterogeneous because they don't mix, they're not mixing. So this could be like oil on top and water on the bottom. But these are all round, so something comparable to that. This one, I don't know. I mean, there are multiple ways. I mean, if you call this a gas, that's fine. If you call this a liquid, that's fine too. That's borderline here. Again, this would be a mixture. We could change the composition of that here. This, I don't know, that looks like a stone, a rock. And a rock is a mixture here. This is sparkling water. Sparkling water, is that a mixture or pure? Yeah, sparkling water is mixture. There's CO2 dissolved in there. This is copper 2 sulfate. Copper 2 sulfate looks to be pure here. So there's some more examples. This is silicon, I think, but it has a gold color to it. This is a crystal of silicon, one big crystal of silicon. It usually has more of a black color, but the photography is a little off. Okay. So we're going to identify some of these as being, okay. Is this a compound or an element? A. Compound or element? Okay. Okay, it's going to be an element. A compound would have to have 2 different elements. So it looks like we have the same. So a compound would have to have 2 different elements like carbon and oxygen or whatever. Is it, it's an element, and so what are the structures of an element? Well, elements can occur as molecules, lattices, or atoms. And so in this case, this would be molecules here. Okay, B. Is B a compound or element? Element, okay, that's good. And what would you call this? Molecules? This would be a lattice, that's correct. C, compound or element? Yeah, C is a compound. Molecules, lattice, or atoms? or molecules here. Right, good. In fact, atoms, it wouldn't make sense because compounds are either going to form molecules or lattices. D, compound or element? For D. D is a compound, good. Molecule or lattice? A lattice. It's a lattice, that's good. It's not a molecule, because molecule would be like a discrete unit here. When I look at a discrete, what is the smallest unit of this? The smallest unit of this looks like one blue and one green. And that one blue and one green, I don't call a molecule, because this blue has different choices of green, and each green has different choices of blue. And so instead of calling this a molecule, I call this what? A formula unit, yeah. This is a formula unit. Let me give you another word for this. In this case, this could also be called an empirical unit. Empirical means the simplest unit. What did empirical mean earlier? This is the second time I'm using empirical, and there are two definitions for empirical. There's this definition of empirical means the simplest unit. The previous definition, that's correct, Diana, that's good. It means it's from observation or based on observation. So empirical is an often used word in science. Over here, this is discrete, and so this would be a molecule here. This is a molecule, but I don't want to confuse you too much. It's also called a formula unit. And so both of these are formula units. So this would be a formula unit of this compound. This would be a formula unit of this compound. This formula unit forms a distinct molecule, whereas this formula unit forms an empirical unit, not a distinct molecule. Here, is this an element or compound, E? Yeah, element is correct. Does this form atoms, lattice, or molecules? Yeah, this forms a lattice. Good. Let's see that. Okay. Let's move on to the next slide here. A. It's hard to see, kind of. Doesn't look so well ordered, but A is a element or compound? A is an element. Is that solid, liquid, or gas? What would your guess be? Liquid? That's fine. I'd accept liquid. Solid, I'll accept. This one, it's hard to tell. I can't tell. There's no motion. And so either solid or liquid. B. Is B an element or compound? This is a little bit of a trick question. Yeah, B is a bit tricky, but you know what I think of B is? I don't think of B as being a compound. I think of B as being a mixture. Let me tell you the reason why I think B is a mixture. I think B is a mixture because what happens if I just remove another one of these purple and replace it with a green? So do you think that's acceptable there? I think that would work. You know, I could have more green balls in there, just substituting, or I could have fewer green balls. And so it looks like it's easy to add more or remove more by just substituting. So this is why I'm leaning towards this is a mixture. Whereas over here, let's say I want to get rid of this green ball and make it a purple ball. Is that something that's easy to do? No, because that's no longer going to be this. It's not so simple. So over here, is this, let me ask you, is this a compound or an element? It's a compound. In this case, it's pure. And so this is a compound. Over here, this is a mixture. Mixtures are mixtures of elements or compounds. Over here, there's a compound, and this would be, would this be a, this wouldn't be a mixture. No, this would not be a mixture because I can't change the amount of green and I can't change the amount of purple because it's always going to come 1 to 1. And so in this particular compound, is this forming molecules or lattice? Yeah, molecules. So this is discrete. That's good. D, element or compound? This element is gaseous, and it's atomic. And this is gaseous. This is looking more solid. You know, it looks better ordered than this a little bit, although this is pretty well ordered. So this is looking solid. You'd expect if this were a liquid, some of these would be tweaked at some angle. You know, you can't see any angles here because they're all balls, but here, these are these cigar-shaped molecules, what they call, and so they could be tweaked at an angle. So this is for sure solid, and this is an element and forms molecules. This is an element that forms atoms. Okay, let's move on here. Looking at this, is this an element or a compound? This is a little bit of a trick question. Is this an element or a compound? Well, it's a compound, but the problem is does this have a fixed composition? No, because this is actually a mixture as well. You know, I could have more waters or I can have more of these. Blue is usually for nitrogen. And so if I have 1 nitrogen and 3 of these hydrogens, we form NH3. NH3, does anybody know what NH3 is called? And these are H2Os. This is a mixture of H2O and NH3. NH3 is called ammonia. Yeah, good, ammonia. So this is ammonia, a mixture of ammonia and water. Probably in the liquid phase. It might be in the gas because everything's so far apart, but usually we have something called aqueous ammonia, ammonia dissolved in water. And so it's a mixture of 2 different compounds, the compound water and the compound ammonia. And these compounds are molecular compounds because they form molecules. See what's happening here. So what's happening here? Can you see? There looks to be a change going from initial to final. It's not liquid to gas, although it kind of looks liquid to gas. That might be a factor there. But what they're trying to show is this a physical change or a chemical change? Yeah, if it's a liquid to gas, it would be a physical change, but this is a chemical change. You can tell it's a chemical change because the atoms got rearranged. Now the blue atoms are with red and the yellows are with the gold. And so we have new compounds here. This is a new compound, molecular compound, new molecular compound from our original molecular compounds here. And so that's the switch. There's a chemical change. Is this pure or a mixture? What did you say? Say this is pure. Actually, mix, pure. Mix. And well, in order to be a mixture, it has to have variable composition. So what can we change? Let's say if I remove some of these, is this molecular or lattice or atoms? What would you say these things are? Molecules, lattice, or atoms? These are molecules. And so one way I can change this is by adding some more molecules or removing some molecules. If I add or remove molecules, does that change the composition of this? No, that's correct. It doesn't change the composition of this. And so it turns out this is not a mixture. This is pure. This is pure. What the heck is this? I don't know what this is. CH2. It looks like CH2Cl2, but the shape is wrong for that. I got to look at what that is. Yeah, this is pure. And it's going to be, it looks to be something like this, CH2Cl2, question mark, question mark. Because chlorine is usually the green, but there's something that it's just not quite right here with this, so I don't know. It's weird. Here's some more of those. This would be in the solid phase. Okay. In order to go from here to here, and so what they're doing is they're separating out the white and the black and the green. So we separate out the white, the blacks, and the green. What type of separation is that? Is that a chemical separation or a physical separation to separate out the elements? This is a compound. This is a molecular compound. So it forms these big molecules here. And so to separate the compound into, what is this? This is the elements. This is a mixture of the elements. And so I have the black are atoms. I have the green and the white, which are molecules. And these are going from compound to elements. This is called a decomposition. So we're decomposing the compound into its elements here. And the question is this a chemical separation or a physical? And you have it. This is a chemical separation here. This is also a chemical separation, except we're not decomposing it to the elements. In this case, here in this decomposition, oh, this is weird. Sorry, this is not, there's no red. In this decomposition here, we're getting different products. So here was complete decomposition into the elements. Here, this decomposition is going into elements, which is the green. The green would be element, but this black with the two whites, that would be compounds. And so in this case, we're getting a compound, the black with the two whites, and an element, the greens here. Here we're getting all elements. And so this is decomposing it into the elements. This is decomposing it into the element plus compound. This, I don't know what they're doing with C. I needed the caption. I didn't write the caption down, sorry. Okay, so let's look at a person here, and we look at the elemental composition of this person. It turns out when we look at the elemental composition of the person, the most common or most abundant is oxygen, that's 65%. And so this person is made up of 65% oxygen, but this is O, not O2, not O2. It's O, that means, actually this O, where does the oxygen come from? It's not in their lungs. The oxygen actually comes from water. And the person has lots of water, mostly water by mass. And so this is why the percentage oxygen's high, because the oxygen's the oxygen in water, not the oxygen in O2. And so here we have atomic oxygen. Here we have the diatomic or molecular oxygen. And 18% carbon, 10% hydrogen. The hydrogen is not H2. You know, the hydrogen is the hydrogen found in water and other species. And then we have nitrogen. This is not N2, like in air. Okay. And so this is this. And so where do these numbers come from here? These numbers come from analysis of a person. So when we look at characterization of matter, the first thing we ask is it's solid, liquid, or gas, or maybe it's heterogeneous. So a person is largely what? Well, actually all three. Solid, you know, the bones. Liquid, you know, like there's blood, other fluids. And then gas in the lungs. So we have all three present, solid, liquid, and gas present. And so when we're looking at it, is a person pure or is a person a mixture? The person's a mixture. And if the person's a mixture, is the person a heterogeneous mixture or a homogeneous mixture? The person would be a heterogeneous mixture. So person's heterogeneous mixture. Sorry if red is hard to see. I forgot to hit this. All right, and so if the person's a mixture, then they're going to be a mixture of a whole bunch of different substances. And so what are the substances? Well, the substances are elements and compounds that the person's made up of. And so when we have a mixture, this is going to be a mixture of elements and compounds. And so we can separate those using physical separation techniques. To the individual components. And so we can break it down. We can separate it into element number one, like say nitrogen or something like that. Element number one. And two in their lungs, you know. Element would be O2 in their lungs. What else do we have? Etc. Or compounds, you know, so what compounds? Well, water is a compound, you know. Proteins. Proteins are another compound. Fats are another compound. Sugars, different sugars, those are other compounds. Yeah, lipids are another word for fats here, so lipids. Yeah. And so we could separate the person into individual, okay. And then once we get the compounds here, we could separate the compounds into elements. So for example, proteins, a lot of proteins consist of carbon, hydrogen, and oxygen, and some other elements, nitrogen, whatever. You can separate that. Fats, a lot of carbon, hydrogen, oxygen, and fats. Sugars, the same thing, a lot of carbon, hydrogen, and oxygen. So we can separate those into, you know, the top three, carbon, hydrogen, and oxygen, or oxygen, carbon, hydrogen. This is top three by mass, not by atoms. You know, is we have to, you know, this is percentage. Percentage, we have different percentages. And so let's take a look at percentages really quick here. If I look at water, here, what is it? Well, it looks like there's 2 hydrogens for every oxygen. So it looks like it's 2/3 water. And so that would be 67% hydrogen. I mean, 2/3 hydrogen. 1/3 oxygen, 33% oxygen. This is by atom. But if we do it by mass, a hydrogen doesn't weigh much. An oxygen weighs 16 times what a hydrogen weighs. So an oxygen is 16 times heavier. If an oxygen is 16 times heavier, it flips this. And so it becomes about 11% hydrogen and about 89% oxygen. This is by mass or by weight. So we have to look at how we look at this. We need to know what these percentages are here. Are they atom percent or are they mass percent? These ones look like mass percent here. And so this is by mass. Well, anyway, we could separate into the individual elements. We can take all these compounds and use chemical separation techniques. like electrolysis. Electrolysis will separate hydrogen from oxygen in water. So we'll get H2 and O2 over here by using chemical separation. And so once they do this, then they can get the breakdown. This is what we call the elemental composition of a person here. Elemental composition by mass. And so a couple of key things here. When we have mixtures, it's very tough. This separation is very tough, you know, physical separations and chemical separations techniques here to do. Okay, but let's do this here. Excuse me, compounds again can be separated or broken down into elements here. And that's what they did here. They broke down all the compounds into elements. And the elements they left as elements. Let's see, we started at 5:13. So, okay, it's time for, can you believe, it's time for another break. No, this is a very long marathon session. And we'll break it up more as we go along, but let's take another break right now. And then we'll start up after the break. This will be our final break, okay? I'm gonna pause the recording here. Okay, we're almost through chapter 2 here, so let me finish it up. When we think about, I was talking about the rules, you know, the rules for chemistry are the same, whether you're dealing with biochemistry or geochemistry, physical chemistry, whatnot. And what are the rules? Well, the basic rule that we follow are deal with electrical forces. You know, the electrical forces are how we understand chemistry, and electrical forces are the most important natural force in chemistry. So there are different forces of nature, like electrical, gravitational. Gravitational is not so significant. You know, if you're working on the moon versus working on Earth, yeah, then it's significant. But anywhere on Earth, it's pretty similar in terms of gravitational pull. So we're okay there. It doesn't change much. And so the electrical forces, like, for example, what is holding two water molecules together? You know, what holds the two water molecules together, I told you, is a hydrogen bond. But what exactly is a hydrogen bond? You know, how would you describe a hydrogen bond? And so when we're trying to describe a hydrogen bond, if I have two water molecules together, they're sticky. And they're sticky because of the hydrogen bonding. They're sticky because of electrical forces that are attracting the two molecules. This is why in that fountain that I was mentioning, even though you get these big blob drops, globular drops, they don't break apart. They don't break apart because the water molecules are stuck together and sticky. They aren't permanently bonded together. You know, it's like a sticky glue, but it's not like a super glue where it's bonded totally. And so that was the hydrogen bond. Even though it's called a bond, it's technically not a bond. A bond is much stronger and a more permanent entity than an intermolecular force is what I'd called those earlier. And so let's take a look at some electrical charges here. These are two pith balls here. When a silk cloth is rubbed on a glass rod, electrons are transferred from the rod to the cloth. So what happens is electrons are negatively charged particles. And so if the silk cloth picks up electrons from the glass, then that means the glass is going to be short of electrons. If the glass is short of electrons, it's lost some of that negative charge, which means it's positively charged. And so the silk, rubbing the silk scarf on this glass rod makes the rod positively charged here. Okay, when the positively charged rod touches two pith balls, it removes some of the electrons from the pith balls, leaving them with a positive charge. So now this rod has lost some electrons. It's going to take the electrons from the pith ball. So what happens is it makes both pith balls positively charged. And what happens is if you have two positive charges, they repel each other. And so you can see the pith balls are trying to stay apart from each other. Well, this is not what's happening in water. In water, they're trying to attract each other. Okay, so if we go here, when fur is rubbed on the rod, then the electrons are transferred from the fur to this rubber rod. And so the fur is losing electrons, so that becomes more positive. And the rubber rod is gaining electrons, which becomes more negative. And so what they can do is they can add some extra electrons to this rubber rod, and the rod touches one of the pith balls here. If it touches one of the pith balls, then what happens is it makes one pith ball negative and the other pith ball positive. And when that happens, they attract each other. So you can see that they're attracting each other here. Here they're just held together by gravity. But here they're pulling up this ball, and it's carrying up this other ball here. So this is going against gravity here. And so this is an attraction. And so what it boils down to is this. You know, electric charge is a physical property of matter. There are only two types of electric charge, positive charge and negative charge. If the two objects have the same charge, they either both positive or both negative, they repel each other. So like charges repel. Here, like charges repel. Now, if you have one that's negative and one that's positive, then unlike charges attract. So Coulomb's law basically says this, you know, like charges repel. Repel. This is from physics. Unlike charges attract. So opposite charges attract. Now, Coulomb's law, this is qualitative here, and so qualitative. We can also do Coulomb's law quantitatively. There's an equation. This is the force of attraction or repulsion is dependent on ZA times ZB divided by D squared. And so if they're opposite in charge, like say A is positive and B is negative, then it's attraction. If they're the same, let's say A is positive, B is positive, or A is negative and B is negative, then it's going to be a repulsion. And so what is Z? Z is the magnitude of charge. Magnitude of charge. So the higher the charge, the bigger the Z. The lower the charge, the smaller the Z. And that's on A, species A. Then we look at species B. And Z would be the charge on species B. Now D is the distance between the center of the charges. And so this is the D. The further apart these charges, the weaker. And it's going to drop off by the square. So it doesn't take, you know, when they're very close, it's going to be a much stronger force. But as soon as you start pulling these apart, the force weakens dramatically because it's squared, D squared there. And so Coulomb's law just tells us, you know, that the force of attraction or the force of repulsion is directly proportional to the charge in each body and inversely proportional to the distance between the centers of charge squared. Here's another example of like charges. Actually, this is an example of unlike charges attracting. And so let's take a look at that here. Just taking a comb and rubbing it on something. And so you can see that these got to be unlike charges. Unlike charges here attract. There. And that attraction will be dictated by the magnitude of the charge. The higher the charge, the stronger, and the distance, the closer they are, the stronger. Now, what happens is the atoms are touching. And since the atoms are touching, the distance people say is 0, they're touching. And so if this is A and this is B, if they're touching like this, then this is, you say the distance is 0, but it's between the centers. And since it's between the centers, it's going to depend on the size. So let's say a B is a much larger atom here. Then the distance is going to be greater. And so what happens is it depends on the size of the atoms. The smaller the atoms, the stronger the attraction. The bigger the atoms, the weaker the attraction. And that's the same for molecules too. You know, the bigger the molecule, the weaker, the smaller the molecule, the stronger the interaction is going to be. We did talk about chemical equations. Let's look at some other examples of chemical equations here. And I'll write up a few of them here. And so one chemical equation is like burning wood. You know, wood consists of cellulose. Cellulose is these kind of glucose. This is called glucose. It's sugar, and it's all linked together. And so this is a solid. And if we burn it, you know, we can burn glucose too. If we burn glucose, we're going to need oxygen. It turns out we're going to need 6 oxygen molecules, O2 molecules. Glucose, this is one big molecule of glucose here. And when we burn this, it ends up forming carbon dioxide, CO2, which is a gas, and water, H2O, which is a liquid. And we end up with needing with six carbon dioxides and 6 waters in this. And so this is a chemical equation here for that. Photosynthesis is the reverse. So this would be like burning wood, and then photosynthesis takes CO2 and water. And so trees would take CO2 gas and water to make glucose or cellulose. Cellulose would just be a long linked up chain of these, and oxygen. So this would be photosynthesis. So this would be burning wood for fuel. This would be making wood, or burning glucose and making glucose here. And so these are examples of chemical reactions or chemical equations. Now, what we're going to do is we're going to throw in one more thing into these equations. So let's take a look at that. And that is energy. When I think about energy in chemical and physical processes like this, when you burn wood, you know, what happens is you get a lot of heat, and that heat is energy. And so what we can do here is, if we want to incorporate energy into this equation as well, I can just add it on at the end. I'll just add it on here. And so one more product of burning wood, and this isn't always done. Sometimes we just look at, you know, what's happening with the atoms. The atoms get rearranged in the chemical reaction. You can see here, and forms new products. But in this first one, we generate energy. If we generate energy, we call it exothermic. So this is exothermic. Energy is what we call a product. And if you recall, on the left here, we have the reactants. And on the right here, we have the products. And energy is a product. It's not always written in a chemical equation. Down here, when we do photosynthesis, the trees get energy from the sun. And so energy is a reactant in photosynthesis. So we have energy from the sun combined with CO2 and water to make the glucose or cellulose and CO2 in this, or not CO2, what am I doing? That's wrong. It doesn't make CO2, it makes O2, oxygen. So let me change that, sorry about that. It should be O2. O2. And so plants do this. They get energy from the sunlight and undergo photosynthesis. This reaction is endothermic. When energy is a reactant, we call it endothermic. It's consuming energy. When energy is a product, we call it exothermic. Now, when we're talking about energy, you know, what is energy? Well, we usually talk about the total energy. The total energy is also called the internal energy. Internal energy gets a symbol U for internal energy. And internal energy, the total energy is a mix. It's the combination of what we call kinetic energy. Kinetic. We heard that word before, kinetic. What was kinetic referring to? Make sure I turned on the recording. Motion, good. Good. And so we have the energy of motion. Okay. We have kinetic energy. Kinetic energy, this is what we call directly proportional to temperature. The higher the temperature, the more energy you have. And so if you cool it down, things become lower energy. As you warm things up, it becomes higher and higher energy. So kinetic energy is related to its temperature. And we have one more, that's potential energy. So the total energy is the sum of the kinetic energy plus the potential energy. This. Now, when we have a change in energy, then there's going to be a change potentially of kinetic energy and a change of potential energy. And so here, when we look at delta U, this is the total change in total energy or the change in internal energy, delta U. It's equal to Q plus W. Q is the symbol for heat. W is the symbol for work. And this is equal to delta kinetic energy, which I'm going to abbreviate KE for kinetic energy, plus delta potential energy, or PE. PE we'll use for potential energy here. Let's see that. Maybe red's not the best color for this. It's hard to see. But let's look at some examples of this here next. Let's see. Okay. How do you access? I'll talk about the recordings in a minute, though. This. Let me clear this and go. Here. We'll just use this slide here. All right. So in terms of energy, this is typically the way we represent it as. We have something called the energy level diagram. And so energy level diagram. And so let's put methane, or not methane. Should we use methane? I'll just use the same. Actually, let's just do glucose. We'll do glucose, C6H12O6 solid, plus 6 oxygens, 6O2 gas. And then in an energy level diagram, we plot energy as a qualitative scale on the left. We don't put any numbers there, so it's not quantitative here, it's qualitative. And so here we have a mixture of glucose and oxygen. Glucose and oxygen, and we're going to have the temperature at room temperature at RT. RT, does anybody recall what the temperature is at room temperature? RT is taken as how many degrees Celsius? I don't know if anybody caught this because I was talking kind of fast. Did you catch it? I mentioned it. 19 would be a little, would be pretty comfortable, but it's not 19. It's a little warm for my taste in the summer, maybe. Oh, maybe in the summer it's perfect. In the winter, it might be a little warm. It's not 19, it's 25. I had mentioned it briefly. It was like 77 Fahrenheit, which is hot for me. It turns out that this is going to form CO2, which is going to be down here, plus H2O, which is going to be down here. And so what this is telling me is a mixture of glucose and oxygen is at a higher energy than CO2 and water. And so glucose and oxygen, that makes sense. It's higher in energy because glucose and oxygen, you can burn the stuff. CO2 and water, can you burn that stuff? Here, it's kind of noisy here. Let me do something. In other words, okay, this is a higher energy mixture here. E for energy, E or U for energy. There's another one, H for energy. This is going to be lower energy. And so when I use E, it's interchangeable with U. E or U, it doesn't matter. Okay, so this is a higher energy mixture. This is a lower energy mixture. And this is the reactant mixture. This is the product mixture. So we're going from higher energy to lower energy in this reaction. So we drop from higher energy to lower energy. Now, there's something called the first law of thermodynamics. Let me write that over here. First law of thermodynamics. Dynamics. Does anybody know the first law of thermodynamics? First law of thermodynamics doesn't have any exceptions. People have been trying to find exceptions to the first law of thermodynamics, but they haven't been successful. The first law of thermodynamics sounds a bit familiar. And so what is it? The first law of thermodynamics says that energy is conserved. That's one way of saying it. Another way of saying it is energy is neither created, neither, created nor destroyed. And so, you can't create or destroy energy, oddly enough. And so this is what happens here. In an exothermic reaction, we start off at higher energy and we go to lower energy. In the process, we drop in energy. Well, how do you lose that energy? Well, you can't lose the energy. Energy is neither created nor destroyed. So we're going to have this at RT, 25 degrees C. So when we burn, what we're going to do is we're going to burn the glucose and then let it cool back down. So the CO2 in the water will cool back down to 25 degrees C. In the process, this releases energy. And so delta E, this is exothermic. And energy is released. When it's exothermic, the delta E is less than 0, so it's negative. We get a drop in energy. We minus, so let's say we lost 1,000 joules joules as a unit of energy, this would be minus 1,000 joules that we just dropped. So this is why it's less than 0 here, exothermic. Delta E. Well, this is the same thing as delta U. I said delta E and delta U are interchangeable. Well, delta U and delta E, we're going to have delta kinetic energy. So was there a change in kinetic energy? Well, if we start off at room temperature and then we end up at room temperature, delta KE is 0. Because the kinetic energy, it's 25 degrees here, it's 25 degrees here, it's the same temperature. It's the same temperature, it's going to be the same motion. So the kinetic energy is the same kind of thing, same overall motion. And so the difference here is in terms of potential energy. And so in terms of potential energy, this is the way we think about it. This is a high potential mixture, chemical potential. This is low chemical potential. We can think of this in terms of a slide, you know, here, gravitational potential. If you're at the top of the slide versus at the bottom of the slide, and let's say the temperature is the same. Let's say this is at 25 degrees C and this is at 25 degrees C here. Then there's no difference in kinetic energy here. What is the difference? The difference is in potential energy, and gravitational potential energy depends on the height you are above the ground, let's say, in this case, or above the center of the earth. And so this person has high energy, right? High energy. And this person has low energy. And the high energy here is all gravitational potential, and the low energy here is all gravitational potential energy. And so if we drop down in energy, then the energy has to go somewhere, right? And so we're going to have a delta E, which is going to equal delta U, which is, where does that energy go? Well, the energy comes from the change in kinetic energy. Here, the change in kinetic energy, well, if we start off at room temperature and we end up at room temperature, then the change in kinetic energy is 0. And so the entire change comes from the change in potential energy. And so there's going to be a change in potential energy because this person's at the top of the slide, this person, and then they go to the bottom of the slide here. And that change in potential energy is, well, it's got to be exothermic because we're dropping down in energy. That means we start off at high energy, go to low energy. Energy cannot be destroyed. And so the energy goes somewhere. And so that's going to go into heat and or work. And so the heat and or the work. Well, this could go into heat easily. So let's convert that change into heat. If we convert that change into heat, what's going to happen is this. The person's going to slide down the slide here and lose energy. And that energy is not really lost. That energy goes someplace. And where did that energy go? That energy went into heat. And so what happens is the surface of the slide gets hot and starts to radiate off heat. And so there's going to be some friction. And so either that, or if there's no friction, they might break a bone when they hit the bottom here. You know, they're going so fast, you know, that'll stop them. But anyway, that energy's got to go somewhere. It's either going to go into their bones when they come to a stop here, or in heat as they friction off that excess energy here. And so this is the case where the energy is converted into heat. Another scenario is, let's say somebody greased the slide. If somebody greased the slide, you better be careful, otherwise you're going to get thrown off the end and maybe end up breaking a bone. Well, if that happens, maybe what you want to do is you want to set up some kind of pulley system. And so if we do that, then we can convert this energy into work like this. If we convert it into work, what we'll do is we'll put the person here. And then let's say somebody greased the slide. And so what we'll do is we'll attach a rope around the person's waist and then attach it to a mass about the same as this. So if this person weighs 50 kilograms, this mass would be 50 kilograms approximately. And then when they slide down here, there's very little friction, you know, because it's a greased slide. And so when they end up at the bottom of the slide, what's going to happen is they're going to pull up the weight. When they pull up the weight here, that's work, you know, to pull up a weight, you know, or lift it off the ground is work. And so in this case, if this were frictionless slide, then they had done the maximum amount of work, raising a weight cost you work. Or it could be a combination of both. There could be some friction and some work done, you know, but we're going to have heat, Q, and work. You know, that's what's going to happen with this. And eventually they're going to cool back down to 25 degrees C. Well, the same thing here. Yes, I'm going to get a change in potential energy. And now this change in potential energy I can use, you know, use to do heat, or I can heat something up. So if I burn the wood, I can heat up a pot of water or cook some food. Or I could do work with this. If I burn the wood, I might be able to run a steam engine, and the steam engine can run a train, which would be work. And so this is going to equal Q plus W, can be converted into heat and or work. The same thing goes for a battery. You know, if I have a battery has a fixed amount of potential energy here, battery at 25. If I discharge that battery, I could discharge it to do work, or I could discharge it to do heat, or a combination of the two, you know, type of thing. Now that's exothermic. Endothermic would be the reverse process of this, you know, rather than going down, we're going to go up. And so photosynthesis would have to, we're going from lower chemical potential to higher chemical potential. Where's that energy coming from? The energy is coming from the sun, you know, and so this will be endothermic here. And the sunlight's going to supply the energy to go up there. Plus, we need enzymes to do this. It's not a simple conversion here, and it's not something easy to do, but the plants can do it here quite easily. All right, when we convert the energy, like I said, energy is neither created nor destroyed. There's lots of different types of work. So for example, this would be mechanical work here. But we could do other work, you know, like breaking a bone, that could be work, or making noise, that could be work, or radiating off heat. Well, radiating off heat is heat in that case. But let's move on to the next thing here.
Professor, when does class end?
6:35 is when class ends.
All right, thank you.
Time is at 6:10 now, yeah. So we have 25 more minutes.
On the Zoom link, it said it ends at 6:05.
Oh, does it end at 6:05? Oops.
Yeah, that's what it said.
Oh, okay, then I was mistaken. Shoot. I needed to finish chapter 2, but it's all right. I'm almost done with chapter 2. Let's see what I have. 2 more slides. All right, next time we'll finish up chapter 2. Yeah, sorry I went over. You're right, it's 6:05. I got it mixed up. 6:35 would be a full 7 hours. Okay, well, your homework today is go back through all your notes and make sure you fill them in, all the missing information, anything that's confusing, make a note of that. And so your homework is to make sure you understand everything that was presented today. That's your goal. And if you don't, then tomorrow ask me about it, okay? But that's your homework for today. We don't want to get behind, and getting behind is pretty difficult to catch up. Okay, now the recording you're going to find on Canvas. So let me just show you, if you want to stick around for the recording, I'll show you how to find the recording here. Okay, that's not it there. Let me see. This would be it here. So if we go to Canvas and you go to Confer Zoom, you hit event recordings here. Let me see if they processed yet, any of them. Monday, check for recordings. All right, it's going to take a little bit more time to process it, the recordings, but the recordings are going to be posted here. Now, I'm also going to post the recordings on, once this is done processing, I'll probably post it on YouTube too. I haven't decided yet, but you can find it there or here. All right. Are there any other questions? We ended? Okay. Yeah, no problem. Amazing. Okay. All right, if there are no other questions, and also if you want to an office time, the offices are by appointment and they're going to be Zoom sessions as well. So you can always do that. And then when you're going through your notes, you can always refer back to the book. I usually go through the notes first and then read, in that order. I never read first because I'm not sure what to focus on. And so I always do notes first and then read. If I read first, it's only by skimming. I never read it thoroughly. I'll just skim the chapter. And then when I do read, I just concentrate on the sections that were covered in lecture, you know, so I understand the stuff that was covered in lecture. Okay. All right, well, anyway, have a nice evening. That was a long marathon, but this is what the course is going to be like, kind of long, very long days. Okay, but we get it over with quick. Can you explain how molecule sizes change electric charge? It doesn't change the charge, it changes something else. And that something else is called charge density. So let me post that here. Oops. When we're looking at Coulomb's law, we think in terms of charge density. Charge density. And the way we use it is like this. Let's say I want to figure out what has a stronger attraction, you know. It turns out that sodium has a positive charge like this. And so it's like a little sphere with a positive charge. And then chlorine has a negative charge like this, and it's a bigger sphere with a negative charge like that. Versus bromine. Bromine has the same charge, it's -1, but the bromine atom is a lot bigger than the chlorine atom. And so in terms of Coulomb's law, which one has a stronger force? It's still stuck on the Canvas screen, okay. Let me, sorry. Let me try this. All right, can you see the drawing now? Yeah, okay, good. All right, in terms of the force, according to Coulomb's law, which one is going to have a stronger force of attraction? These are opposites. This with this, or this with this. Well, it also depends on the distance. So what we're going to do is we're going to bring them both right next to each other. In fact, we're going to let them touch. And so if I let them touch, this is what it's going to look like, because, you know, this distance is going to offset the whatever. And so here, this would be a sodium with a chloride, what we call chloride, like that. This would be a formula unit. A formula unit, I'll abbreviate FU. This is a single formula unit of sodium chloride. And then we look at sodium. This is called sodium bromide, and we look at a formula unit of sodium bromide. And what holds these together is a bond. There's a bond here. Which bond is stronger according to Coulomb's law? Sodium chloride or sodium bromide? Well, you might say, oh, they're the same charge. They're the same charge. They're going to have the same strength. But they don't. One of these is stronger. And which one's stronger depends on the distance. But, you know, pretty soon we're going to stop thinking like that a little bit. And so it's the distance between the centers. So if I look at the distance between the centers, yeah, sodium chloride is shorter distance. So this is the stronger bond. This is the weaker bond. That's how I do it. But the way I do this normally is I visualize these two things differently. I visualize these in terms of charge density. So in terms of charge density, it looks like this. If I look at the negative charge is distributed over this entire sphere here. And so the negative charge is distributed. Now I have the same number of dots here, but I have to distribute it over a larger volume because it's the same negative charge. And so what we see is here, the charge is more concentrated. Charge is more concentrated. In chloride. The charge is less concentrated in bromide. Less concentrated. And so what this means is that this has a higher charge density. Chloride has a higher charge density, meaning it's going to have a stronger Coulombic attraction. And so increasing charge density. And then this has lower charge density. And so the size of the atom, to me, means the charge density. Big atoms, low charge density. Small atoms, high charge density for a given charge. Now, some of these atoms can have higher charges, like rather than a negative charge, it could have a -2 charge, like that. Okay, does that answer the question about the size? The molecules do the same thing. When we have a charged molecule, we call it a polyatomic ion. And so it's the same kind of deal, you know. It depends on the how big it is and how spread out it is. And so big molecules, low charge density, small molecules with a charge, high charge density. Okay, great. Okay. Were there any other questions? All right, well, thanks for sticking it out. Did anybody come in late? Okay. No? All right.
Yes.
Oh, I'm sorry, can you repeat?
Yeah, I came in late, Stephanie Choi.
Okay, Stephanie, did you get, did I call you on the roll?
No.
Okay, let me do that really quick here. Okay, I have you here. Stephanie, what's your major?
Biology.
Bio, okay. All right, thanks. Did anybody else come in late? Stephanie, was it clear how to get here? Was there any issue with the logging into Canvas or Conference Zoom?
No issue.
All right. Okay. Cardo. Are you on the wait list, Julian? Cardo. Oh yeah, no, I got you here, Cardano. Oh, what's your major? Is it Julian or Julian? Or how do you pronounce it? If you hit the space bar, Julian, okay. If you hit the space bar, you can go off mute as well. What's your major, Julian?
Kinesiology.
Kines, okay. Were there any issues launching Zoom?
No, they were not. I just never used Zoom, so I just had to download it.
Okay. Okay, anybody else come in late? All right, well, thanks for sticking it out here, this 7 hours or so. And we'll see you guys tomorrow morning. Okay, thank you. Gonna pause. stop the recording.